All right, everyone, this is lesson 41, rate in and rate out, also known as net change. When you integrate a rate, you get net change, all right? So one version of the fundamental theorem of calculus looks like this. And you can see here, this is rate in minus rate out, all right? So to find the amount at a certain time, we use these two functions here, all right? That's the original amount plus the amount in minus the amount out. That's known as our rate in minus the rate out, all right? How do we get that? Well, right below, original amount plus the integral from t equals 0, let's say, to t equals whatever, another t value, right? And then that's the rate in function minus the rate out function, also with the integral there. So let's look at an example. This example is given to us by AP Classroom in AP Calculus AB, all right? And it says here that a non-traditional confectionery plant contains a chocolate pond that is being supplied by a chocolate river. Starting at 9 a.m., there are 1,000 gallons of chocolate in the pond, and the river is depositing more chocolate into the pond at a constant rate of 60 gallons per hour. All right, so the chocolate is being pumped out of the pond to various parts of the plant at a rate modeled by the function L of t, also in gallons per hour, and t is the number of hours since 9 a.m. So if we had to evaluate the definite integral of 0 to 8 L of t dt, this would definitely be a calculator active question. You notice what this function looks like. All right, so we're going to go ahead and put this into our calculator, this L of t function. All right, you can go ahead and save that in your calculators like y1 or wherever you want to put it, okay? And I'm going to go ahead and put into my calculator the definite integral from 0 to 8, and that would be L of t dt. All right. So when I put that in my calculator, I'm going to hit math, and I'm going to hit 9, and I'll just go ahead and go from 0 to 8. I have this L of t function saved in y1, so I'm going to go ahead and hit alpha, f of 4, that's y1, and I'm going to hit dx, all right? This should give me the definite integral. That's 464, all right? So the catch here is it does say, using the correct unit, interpret your answer in the context of the problem. So what is 464? Well, this represents gallons, okay? This represents gallons that were being pumped out of the pond from a time of 0 to a time of 8. And that's what we want to write down, okay? So 464 gallons were pumped out of the pond from t equals 0 to t equals 8. All righty? Really important that you answer all of that question. All right, let's go ahead and look at the next question, which would be question B. All right, evaluate L prime of 5. Well, remember, L of t is the function that we have in our calculators. So if I'm going to evaluate L prime of 5, well, then that just goes into my calculator as well. All right, let's see. And I'm going to be doing a derivative this time. So let's hit math. This time we'll hit number 8. All right, that's d dx. We go to the right. We get to put our function in there. So that's my y1 function. And then here, I want to evaluate this function specifically, or this derivative function, at 5. Okay, so when we plug that in, notice that we get negative 5.5536. I'm going to write all of that. Negative 5.5536. That's how you can find that derivative of the rate out function, okay? Now, look at this next question. Is the amount of chocolate in the pond increasing or decreasing at a time of 4? Well, the thing is that when we see the terms increasing or decreasing, we normally think, oh, derivatives are positive, that's when it's increasing. Derivatives are negative, that's when the function is decreasing. Well, the thing is, we haven't quite written that amount function yet. So let's go take a minute and write that out, okay? So the amount function, also known as A of t, in this case would be equal to the original amount of chocolate, that's 1,000, all right? And that's plus the rate in. Well, remember that chocolate is being pumped. Let's draw this out for a second. Chocolate is being pumped into a pond that already has 1,000 gallons of chocolate, all right, at a starting time of 9 a.m. So that means that at 9 a.m., that's a time of 0, okay? So anyway, chocolate is being pumped into this pond, and the rate at which it's being pumped is 60 gallons per hour. Now, chocolate is also being removed from this pond into different parts of the factory at a rate of that L of T function, also in gallons per hour, right? So that's also really important that we recognize, okay? What that means is that there's a rate in and a rate out function that's happening here. Now, 60 gallons per hour, that just means 60 T, all right? But this rate out, well, that's going to play an important role. So let's write this amount function, okay? All right, so let's see. We got, technically, we got an amount function, which is the original amount plus the rate in from 0 to T. I'm going to write here 60 dt minus the rate out, which is from 0 to T also, and that's that L of T function, okay? Now, if I were to integrate this, I mean, I just get 60 T, right? But if I were to integrate this, no, that would be a little bit different, right? So let's put here from 0 to T, L of T dt. We did that already, right? It would depend on the time. Okay, so this is our amount function right there. Okay, now that we have that amount function, now let's think about what increasing and decreasing means. Remember, that means when your derivative is positive or when your derivative is negative. So we might want to take the derivative of this amount function. If we derive this right side, we'll have the derivative of the amount function, okay? So let's see, if we derive 1,000, well, we're going to get 0. If we derive 60t, we'll get 60. And if we derive this L of t and definite integral here, well, this is a rate, right? Integrating a rate, you're just going to get this L of t. Notice what we get here. We get rate in minus rate out, okay? And that's that derivative. That's very important to recognize, rate in minus rate out, okay? It's almost like the main idea of this lesson here today, okay? Now, what we want to know is this derivative at 4, is it going to be positive? Because that would indicate that at 4, chocolate's increasing. Or is this derivative actually negative, in which case it'll be decreasing? By it, I mean the chocolate in the pond, okay? All right, so let's see. Let's take our amount function and let's plug in our derivative of the amount function, and let's plug in 4, okay? Now, I don't exactly have that in the calculator yet, but I do have L of t, right? That's y1. So I'm going to put 60 minus y1, and that's my alpha and my f4 up here, okay? And by opening a parentheses right after that, I can take that y1 function and automatically just plug in 4. So there it is, rate in minus the rate out being plugged in with 4. And notice we get 2, okay? So 2 is a prime of 4, okay? So let's write that out. This is 2. And 2 is positive. It's a positive number. And that indicates that at a time of 4, the amount of chocolate in the pond is increasing, okay? So let's write that out somehow. It does say to justify, and that would basically be because a prime of 4 is greater than 0. So let's write a little bit of that. So the amount of chocolate is increasing, and I'm going to write here because a prime of 4 is greater than 0, okay? Nice and simple. All right, let's look at question D. Question D says, set up but do not evaluate an integral expression for the average rate, ooh, there's that word, average, and then rate, at which the chocolate was pumped out of the pond during the intervals from 2 to 6. Okay, well, I have a new set of intervals now, right? No longer working just from 0 to t. So, all right, and I only want to focus on when it was being pumped out, which is that L of t function. So since it says average rate, that's our average rate of change, okay? This is going to be 1 over that b minus a, all right? So I'm going to put here 6 minus 2. Then I got that integral that goes from 2 to 6. And then since I'm focusing on the function of when the chocolate was being pumped out, that's our L of t function right there. All right, so there you go. This is how we can write that out. This is the setup of that integral expression, but not the evaluated, because we don't have to evaluate this one. All right, let's keep going. This question also has a couple more parts. How much chocolate is in the pond at a time of 8? Show the work that leads to your answer. How much? That's like an amount. You see? How much? That's kind of like an amount. All right, so when I think of that, I'm thinking about my amount function. All right, so let's see. Let's go back and use our amount function, but we'll be plugging in 8, okay? Remember, our amount function was the original amount, right? Plus, and then we had the definite integral that went from 0 to t. Well, this time we know that t is 8, so I'm going to go ahead and write here from 0 to 8. Remember that we had 60 in here, so 60 dt. And then we have on the other part there minus the rate out from 0 to 8 L of t dt, okay? And that just goes in the calculator also. All right, so show the work that leads to your answer. That would be this, okay? All right, here we go. Let's throw this in the calculator. We have 1,000 plus math 9, right? We're going to set up a definite integral. We're going to go from 0 to 8. And we'll go ahead and put here 60 dt, right? Okay, and then minus, we'll do this again, the definite integral, so math 9 again, this time from 0 to 8 still, but the function that we use is the L of t, and remember that's in y1. So you notice how many times we've had to use this function? That's why it's a super awesome tip to always save that in your calculator, so you don't find yourself retyping that, 10 times during an FRQ, okay? All right, we're gonna hit enter. Let's see what we got. 1,016, and what does this represent? It represents how much chocolate, so I guess we can say gallons here, okay? All right, let's write this out as 1,016 gallons of chocolate, okay? All right, that's super important. Let's look at the next question and our final question here. During the interval from 0 to 8, when, we're looking for a t value, okay? When is the amount of chocolate in the pond at a maximum? Oh my goodness, this question is loaded. So when we think maximums or minimums, and I'll be a little bit not as formal here, we are really thinking about critical points. And remember that that happens when your derivatives are 0, or even when your derivatives are like undefined, okay? So I want to go in here and I want to take a derivative, right? A derivative of what? That's what I know so far. Okay, well, let's think back. What are we looking for? When, okay, so we're looking for a t value, right? When the amount of chocolate, oh, we have an amount function. You think maybe we could take the derivative of our amount function? And yes, that's exactly what we want to do. We want to know when our amount function has a derivative that equals to 0. That's what we're looking for. And a lot of times just writing that in your work on that FRQ could even get you a point, okay? So that's because that gives you to a critical point, all right? Anyway, remember we did obtain A prime earlier, right? We did obtain that A prime of t was rate in minus rate out. We did that earlier, 60 minus L of t. We said earlier that was A prime, okay? And now we just want to know when it equals to 0. So what I want to do here is add L of t on both sides, just because I already have it in my calculator, right? I'm going to get rid of this so that it's 60 equals L of t. And I want to know when my y1 function is going to equal to 60. That's what I want to know. Okay, so here's how we do this. This is our candidates test, all right? And because it's our candidates test, this one is the moneymaker on the FRQ, all right? So keep that in mind. Here we're going to be putting this in our calculator, and we're going to be calculating the intersections, all right? Okay, so remember that we already have L of t in our calculator, all right? And that's right here. I have it as y1. I'm going to go into y2, and I'll plug in 60. Okay, now also in the question is during the interval from 0 to 8. So I'm going to go to window, and I'm going to just, well, first thing, just a tip for anybody who doesn't know, you can always hit zoom, and you can always hit standard, and it always graph you out in the standard window, right? But you notice that I really can't see anything in my graph. You can also hit zoom, and you can also hit fit, but you don't see that on the menu, right? And that's because it's so far down that it's all the way down here, okay? when you hit zoom fit, a lot of the times you'll get some values. And you can see there's that y equals 60, all right? And that curve, well, that's my L of t function, all right? So this obviously intersects at quite a few times. But we only care to see where it intersects from 0 to 8, okay? So I have to look at the window here to see where the graph put this into view. But I don't need to go way out far. I really just need to go maybe a little bit past 0 and maybe a little bit past 8. So I'm going to go to window now. And I'm going to adjust this X window, okay? I want to go from -1 just to leave myself a little room. And instead of going to 8, I'll go a little bit further to 9. That should be plenty. I don't want to mess with the Y's because we had a nice view of everything that intersected, right? So when you hit graph, hopefully you can see everything up close, right? Perfect. Okay, so when we're doing our candidates test, we want to know when A prime is 0, right? But what does this tell me? This tells me when the amount of chocolate is at a maximum, okay? So this is really a candidates test, and that means that I'm looking for a time when the amount of chocolate is at a maximum. I'm looking for a maximum at the end of the day, okay? Now, candidates tests, you want to include your endpoints here. So we want to include 0 and we want to include 8. But now we're going to see where these two functions intersect, okay? All right, so let's see here. Let's go ahead and calculate these intersections. So I'm going to hit second and calculate, and we'll be calculating intersections. So first curve, you need to select the first curve. Notice now I'm on the second curve and it's red. Okay, perfect. And now I'm going to see what this point is right there. There we go. Okay, I got 3.7436. All right, let's write that down. That's going to be one of my candidates, okay? 3.7436. I can just write it like this, okay? And now I want to test out the other one. Now that might be a little bit past 8, but let's check it just to be safe, okay? Calculate the intersection, and this is where going a little bit past is actually a downfall, right? Okay, so first curve, as you go left to right, you'll notice you're on the blue curve, and hit enter. Second curve, now you notice you're on the red curve. Okay, perfect. Is this actually an intersection that's between 0 and 8? Let's find out. Nope, a little bit past 8. We want to ignore this one, okay? All right, let's do it again. We got one more a little bit close to the origin there. So I'm going to look for that intersection. All right, first curve. Notice I'm still on that blue curve. Okay, hit enter. Second curve. Now I'm back to the red one. Perfect. I've selected both curves at this point. And now where it says guess, I just got to hover all the way over to that last intersection point that I have not tested yet, right? Okay, I think it's here. Hit enter and it'll recalibrate. And we get 0.2563. Okay, so I'm just going to go ahead and write 0.256, all right? Okay, so now let's go ahead and fill out the amount values, okay? So do we know how much chocolate is in the pond at a time of 0? Well, that should be pretty easy to find. Remember that starting at 9 a.m., there was 1,000 gallons in the pond. It's pretty simple, right? So that one's given. Okay, how about at a time of 8? How much chocolate was in the pond? And if that sounds familiar, it should. This happens a lot on FRQs. Go back to one of your previous parts there. How much chocolate is in the pond at a time of 8? Oh, there it is. We found that answer, right? Okay, so that's 1,016 gallons. Awesome. So if you look at what you really have to do is you really have to just get these two outputs and find out which one is the biggest. So, all right, let's keep going. So now we're going to do this in the calculator, but all we're going to do is we're going to select that last line that we did because we had it with the amount function, but you notice that we plugged in 8 right there for that upper limit, right? So I want to select that because, I mean, I don't want to have to retype all this over and over again, you know? So I'm going to go right here to where my, my upper limit is. I'll select delete, and now the box becomes blank, okay? And I want to go ahead and put 3.743 in there. Okay, now I want to keep going back a little bit more to the other upper limit, which is this one here. And I'm also going to do the same thing, delete, and I'll go ahead and put 3.743. And when you do that, notice that now you have an amount function, but this time with yourself evaluating 3.743. So that saves you a lot of time as well. Okay, when you hit enter, you should get 982.279. I want to write that one down. Okay, so let's see, that's 982.279. All right, and I want to do this one more time because we have another candidate to test, right? So just do the same thing we just did, right? And I actually think it's easier, so you don't have to delete all those decimals. Just going to select the easy one, okay? All right, there it is. Delete that upper limit, and this time we're putting in 0.256. You put 0.256. You don't have to put the 0. Okay, and now I'm going to go back to this upper limit here. Oops, I went too far. There we go. And I'll do the same thing, 0.256. All right, so when we hit enter, we get the amount of chocolate in the pond at a time of 0.256, which, if you think about it, just right after 0, right? Okay, so let's write that down. That number might make a little bit more sense after I said that. 1,000.255. Let's just make these zeros bigger. That's going to bug me. 1,000. All right. Okay, so now which one is the maximum, right? At what time is the amount of chocolate a maximum? That happens here, right? That's our biggest amount value. So that happens at a time of 8, all right? And that's what we have to answer. At what time does that happen? So let's write here at t equals 8, the chocolate is at a maximum, or the amount of chocolate is at a maximum, okay? All right, and that's all it is. You see the candidates test there? So that's really important. A lot of times on FRQs, just taking that derivative and making it equal to 0, that's 1 point. So even something like this could get you that point, all right? If you wrote it out like this, that's fine too, because that represents that a prime of t, okay? So either one of those would be linked to point number 1. Getting your candidates could be point number 2, and obviously coming up with that answer could even be point number 3. This is a big one here that could get us some points. All right. Okay, that wraps up lesson 41. I hope it wasn't too crazy. A few more to go.